Welcome back, everyone, and welcome to our second new episode of Mathical Math with Stories. In this episode, after the introduction to numbers in episode 1, we're going to look at numbers in more depth by investigating a very particular type of numbers, primes. So you may have heard of primes somewhere or delved deeply into primes at some point in your mathematical career. So today let's focus on primes, their properties, and why they're so important in modern mathematics and our understanding. So let's start off with a definition. When we want to investigate something in math, we always look at its definition first. What is a prime? So by definition, the definition is that a prime p can only be divided by 1 and p itself. So p can only be divided by 1 and p itself. So to give an example, we can look at some regular integers such as 5. Is 5 a prime? So we can see that 5 has factors 1 and 5 only. So yes, 5 is a prime. And what about 13? Well, 13 only has divisors 1 and 13, so yes, 13 is a prime. Then you may ask, what about 24? 24 has a lot of divisors, for example, 1, 2, 3, 4, 6, and so on. And apparently it has more divisors than just 1 itself, so unfortunately 24 is not a prime. So review this definition. If p is a prime, the convention is to write a prime as p, denote a prime as p. Then a set of divisors consists only of 1 and p itself. 1 and p itself. So a natural question that rises is that is 1 a prime? Well, you may argue for this question that, yes, apparently 1 divides 1, and also it can be divided by 1 itself, which is also 1. So this is a tricky word problem rather than just a math problem. But in math, we can define anything that we want to. So we're going to say that no, 1 is not a prime. For the sake that, first of all, 1 is special enough because it is the multiplicative identity n times 1 equals 1, which is a special enough property. And also, 1 doesn't adhere with some of the interesting properties of primality that we will see later on. So keep in mind that 1 is not a prime when counting your primes, and we're all good. And second off, let's look at why we choose to talk about primes in our second episode. So when mathematicians investigate some new thing they have thought about, be it primes, numbers, arithmetic, or even some more complex algebraic operations, they always ask, well, do they have good properties? And primes are a very prime example, ignore the pun, that has good properties. So you see that it only has 2 divisors, 1 and itself, and that is a very good property indeed, because when we start counting divisors of some increasingly large numbers, they start to get out of hand. So the first reason for primes is that they have good properties, many of which we will see later on in this video. And second, primes, when you think about it, are the building blocks of the entire system of integers. Why this one? Well, we'll go into it in a bit more depth later in the section on prime factorization, but keep in mind that you can always form any integer by multiplying primes. Take 24, for example. I hate my iPad. Take 24, for example. Well, we can say that 24 equals 3 times 8, and 8 equals 2 times 2 times 2. And then we have successively dismembered 24 into a product of primes, 2 cubed times 3. So in a sense, primes are the generators of the integers. And if you're unsure why I use this terminology here, maybe it will become more clear later on when we introduce generators in a more general algebraic sense. So enough about the definition of primes, let's move on to the study of primes itself. So we have primes, we know the definition, and what should we do with them? How can we discover all those fascinating properties that made mathematicians so obsessed with primes? So let's first look at what questions we ask in math. How many are them? how many primes are there. And how to find primes. If I give you a given number, how can I tell that it is a prime or it isn't a prime? And how to use primes. Primes are awesome, apparently, but if you're not a strict mathematician that is obsessed with numbers, how can we use primes in our daily life? And ignore this fourth one, you'll get it someday. So let's look at these questions in depth. First of all, let's start off with how many. Because apparently counting is the easiest mathematical operation there is, and anyway, it's the first mathematical operation you've ever learned. So how many primes are there? Well, we can try to list them. So the first prime is 2, as you may have learned in elementary or middle school math. Easy. And the next prime is 3, 5, 7, 11, 13, and so on and so forth. In fact, we can list all the prime numbers up to 100, but I would not do that here because that would be a lot of primes. And this sequence of primes seems to go on forever, but actually, does it though? So, our question here is, are there infinitely many primes? Or are there finitely many primes, meaning that there is a limited amount of primes? Now, this is where things start to get tricky. You may think that, well, we can keep listing primes until maybe we reach an end or conclude that the end is not reachable. Well, what do you think? So take a moment to think about it. Do you believe that there are infinitely many primes or finitely many primes? I can show you an argument for both. First of all, infinitely many because it's intuitive, prime seems to go on forever, but finitely many, what's an argument for that? Well, I may say that, well, as numbers get larger, there also tend to be more primes because we have observed them in smaller numbers. So it's going to be harder, in a sense, to find primes that divide numbers because as we go for larger numbers, there are more of them than the existing primes could cover. So that's an argument for finitely many primes. So take a moment to think if there are finitely or infinitely many primes. I'll tell you the answer shortly. Okay, so you may have to think about it for a while, and here is the final conclusion. There are infinitely many primes. But wait, after our first episode, you might just have the mathematical sense to say that you cannot just not state a statement. You have to prove it before you can state it. Well, here's a proof. But how can we prove that there are infinitely many something? So thanks to Euclid, the great mathematician master of ancient Greek times, we have this beautiful proof by contradiction, as we have introduced in episode 1. If you don't know what contradiction is yet, go search it up or look for my explanation in our first video. Thanks to Euclid, we have this beautiful proof by contradiction that there are infinitely many primes. And what we do when we first start a proof by contradiction, we suppose that what we're going to prove is wrong. Suppose, for a contradiction, that there are finitely many primes. We're going to assume the opposite of what we're trying to prove, finitely many primes. But it maybe seems counterintuitive, but bear with me. Then we can write all the primes out. We can enumerate all the primes because there are finitely many. So let's call the primes prime 1, prime 2, p3, so on and so forth, up to the greatest prime p sub n. And those are aligned in increasing order. Because, as we suppose, there are finitely many primes, so there is a biggest prime, namely p sub n. And our contradiction is going to find a bigger prime. So how do we form a bigger prime? We multiply everything in this set of known primes, and we obtain the p1, p2, all the way up to pn, which is apparently not a prime. It is composite because every single prime that exists divides this new integer. However, what if we add 1? So take a look at this. Take a look at this new integer we just formed. Is it divisible by p1? Well, it is not divisible by p1 because p1 divides this integer minus 1. p1 divides this part of the integer, so it cannot divide this integer plus 1. The same goes for p2. p2 cannot divide p1, p2 to pn plus 1 because it already divides p1, p2 times all the way up to pn. And the same argument stands for every single prime in this set. So we have shown that this p1 times p2 all the way up to pn plus 1 is not divisible by any existing prime. It is not divisible by any existing prime. And what does that mean? It means that this product plus 1, p1 times p2 plus times pn plus 1 is prime. Because the definition of prime is that it cannot be divided by anything other than itself and 1. And that is exactly the case for this product times 1. So this is prime. And what implications does that have? Well, if we look at this product, p1, p2, all the way up to pn plus 1, it is definitely greater than p sub n, because all the primes are apparently positive. And they multiply out to be apparently far bigger than p sub n, giving our important contradiction. Because we have assumed here, right here, the red arrow, that p sub n is the largest prime. However, we have found a prime, p1 times p2 times all the way up to pn plus 1, that is greater than pn, greater than the biggest prime. So our initial supposition, suppose that there are finitely many primes, cannot be true. Therefore, there are infinitely many primes. There are infinitely many primes. So take a moment to appreciate the beauty of this proof. This is really one of the earlier proofs by contradiction there is, and through this proof we can acknowledge better just how beautiful and how useful the proof of contradiction is, especially when you're approaching problems that seem extremely hard to prove at first. For example, you want to prove that there's infinitely many of something. This is a really common line of thought if you approach for complex problems. So if you want to prove there are infinitely many something, then we can use a contradiction to say, well, I don't think so. I think there are finitely many of something. Then we derive a contradiction by finding something that's bigger than the biggest one, or, on the other side, smaller than the smallest one. But that's enough yapping about how many primes are there. And we're going to move on to our second question that mathematicians like to ask when they approach a new topic. How to find primes. Well, finding primes as itself is a task that's not extremely hard. For example, if I give you a certain number, can you verify that it's a prime? For example, 38. Is 38 a prime? Well, you're going to say that 38 is not a prime. Why? Because it's 2 times 19. And it has more factors than just 1 and 38 itself. So you're not a prime. Sorry, 38. And what if I give you a hard example, for example, like 91? So you may think that 91 is a prime, but remember it's 13 times 7. So unfortunately, although you seem very prime, 91 is also not a prime. And we can verify the primes we already know. Is 17 a prime? 17 is a prime, because when we look at all the integers from 1 up to 16, none of them divide 17. And the same goes for any prime we want. And there is a really special method on how you can find all the primes less than or equal to n. It is called the sieve of Eratosthenes. The sieve, which is something you use to sift flour in the kitchen, of Eratosthenes. I hope I spelled that one right. Anyway, Eratosthenes was a great Greek thinker and mathematician in ancient Greek. Philosophy and math went side by side, and he came up with this little method to find all the primes less than or equal to n. So we take n equals 100 in this case, and we're going to look at how to use a sieve of Eratosthenes to find all the primes less than or equal to 100. I'm going to walk you through this one. So we have some known primes there. For example, 2 is a prime. We're going to denote primes with a red circle in this graph. 3 is a prime. 5 is a known prime. 7 is a known prime if you have any common arithmetic sense. And what do? So first of all, we take a different color pen and we cross out all the multiples of 2. So this line goes out because it ends in 2. So does this one. those columns are gone right now. We're going to cross out all the integers that is a multiple of our first known prime, which is 2. So those are gone. I'm sorry. And the second part is to cross out every integer that is a product of our second known prime, which is 3. And this is a bit slower process, but bear with me. Okay, so I'm pretty sure that's all of them. So we have crossed out every known multiple of 3 from 1 to 100. And let's move on to our next known prime. Our next known prime is 5. And this prime, we're going to cross out all the multiples of 5 from 1 to 100, at least the ones that are not already crossed out anyway. So this column is entirely gone. All that ends with 5. And the same goes for 7. Let's cross out all the multiples of 7 from 1 to 100, and this is going to get increasingly harder as we get increasingly larger, but bear with me. Okay, I'm fairly sure I got all of them. Let's move on to our next known prime, which is 11. So basically, you might ask, what if we ran out of known primes? What if I don't know that 11 is a prime? Well, using the sieve of Eratosthenes, you just go on to the next number that has not been crossed out yet, which will eventually turn out to be a prime, as you can see why. So let's cross out all the multiples of 11, and this task just gets easier as we cross out more numbers. Anything that's on a diagonal, I'm pretty sure they're all gone right now. And right, so there are no more multiples of 11. What about 13? Are there any multiples of 13 left? 13. So I'm fairly sure that there are no multiples of 13 left. So we can proceed and say that 13 is a prime. So it's 17, wrong color pen, try again. 17, 19, 23, the rest are crossed out, 29, 31, 37. 37 is a good number. And we have 41, 43, 47, and check your mind if you know that these are all primes, 53, 59, because we're just going at this point because apparently there are no more multiples of these known primes left from 1 to 100, because at this point these just get sufficiently large enough. Then we have 61 and 67, 71, 79, 83, wait, I missed 85, don't worry. And we have 89 and 97. So those in the red circles are all our primes from 1 to 100, found using the method of the sieve of Eratosthenes. So a bit of recap right here. The sieve of Eratosthenes basically says that you go from the first smallest number except from 1, because 1 is out of the question in this one, which is we start with 2, and we cross out all the multiples of that number and move on to the next number that is not crossed out, which is 3. And we do the entire process again until every possible multiple has been eliminated, and you are left with the primes from 1 to any number desired, which is a good thing. There are prime tables to up to extremely large numbers, like 5,000, I believe. There are some of them in very antique, ancient, and beautiful math books. You can go look for them if you are starting to become a fan of primes. But I'm not going to find all of those. Instead, we're going to talk about the verification of primes a little bit before we move on to our next slide. The verification of primes. And why do I write that here? Because right here with these arithmetic, we have verified some small primes, which is 17 and anything around, well, what is the definition of small anyway? You might say that anything under 100 is considered small by your standards. However, mathematicians have a really different standard for small, and they don't consider numbers big until their number of digits can be expressed as factors of powers of 2, 2 times n. And why do we focus on this one? For example, if I give you a number with 2 to the power of 16 digits, I give you this, and I want you to verify if it's a prime. And you might say, well, I don't want to do that. But what if I give you $100,000? Well, you may say, I'm going to do that for $100,000. So let's start with looking at whether this number is a prime, is odd, or even. So unfortunately, it's not even because that will make your job so much easier. So it's not even. And then you think, well, is it a multiple of 3? So you try to divide this giant number by 3, which is going to take you a lot of time, definitely. And you found out that it's not a multiple of 3. Then what about 5? And you try to divide this number of 5. And you go on to verify every prime that is smaller than this 2 to the power 16 digit integer, or at least all the primes up to the square root of this, and we'll explain why later. Which is going to take you, frankly, so much time that you probably need the lifetime number of a cat. You're going to need 9 lives to verify whether or not this random integer is a prime or not. And you say, well, this is too hard. I'm not going to waste my time, and I'm going to write a computer program. I'm going to write a computer program to verify that whether or not this is a prime. However, at this point, computers aren't really so much better, significantly much better humans at detecting whether or not a given number is a prime. It often takes computers significantly amount of time because of this fact, I quote, factoring is hard. If you have done factoring exercises in elementary and middle school, you'll probably agree that factoring is hard. And the same goes for computers. A computer has to verify factors if it does things the human way, or there are algorithms to verify whether or not a factor is a factor of a given integer. However, we can always say that, yes, factoring is hard, regardless for humans or computers. But why do I say this? Because this verification of primes, verification of big primes to be particular, is actually the cornerstone of our modern cryptography establishment. This word, cryptography. So, for example, your password, your key construction, everything precious you hold on the internet that is locked behind your password relies on the verification of primes and the sole fact that factoring is hard. I won't go into the mechanisms behind verification of primes specifically. That's a thing for another day in another video. But take some time to appreciate this and maybe to look it up if you like this type of content. And we'll take a brief break before we move on to the next section. Okay, so we have looked enough at primes, their definitions, and their properties, and now we're going to have a brief look on how to use primes. So, a key use of primes is in factorization of integers. So, obviously, the word factorization comes from the word factors. So, it means that we're going to split up integers into their prime factors, numbers that multiply up into the integer we desire. And we're going to look at prime factorization with an example. So, for example, we take the number 24. We want to divide 24 up into a multiplication of prime factors. So, the first step is to test prime factors that we already know. So we're going to say that yes, 24 is a multiple of 2. So we divide it by 2. So this is called short division in opposition to long division. At least it's in my language. I don't really know if they call it short division in other places. So we have 24 divided by 2 and it becomes 12. Then we say that, well, 12 is divisible by 2 also, and we have 6. We write 6 here. And 6 we can easily decompose into the product of 2 primes, which is 2 and 3. So we write 24 as 2 times 2 times 2 times 3, which is 2 cubed times 3, which is the prime factorization of 24. So as we can see here, prime factorization really takes an integer and finds all its prime factors and multiply up. And what does this mean? why do we want to know about prime factorization? So there is a theorem called the fundamental theorem of algebra. I don't think it's algebra. Actually, it's arithmetic. The fundamental theorem of arithmetic. It tells us a bit more about this prime factorization and how it works, the structure behind it. So the fundamental theorem of arithmetic states that for every integer n, the prime factorization of n is unique. Prime factorization is unique. And you might be questioning this, or maybe not, because intuitively, if you know a bit about prime factorization, you will think that definitely, of course, it's unique. And we're going to prove this in another video because time's running out for us. And this is really just a statement on how prime factorization works. And we can have it from the general form of prime factorization. If we have integer n, we write it as p sub 1 to the power of alpha sub 1, p sub 2 to the power of alpha sub 2, so on and so forth, until p sub k to the power of alpha sub k. So if you someday see this sort of form, know that it's expressing a prime factorization, and we're going to look at prime factorization and its applications in future videos. Alright, so we look at plenty of primes, their properties, and how to use them. And you know that math is all about asking questions, so let's ask some more questions about primes. And I have a question for you if you haven't settled one yet. Are there any particular primes with interesting properties? And we know that in math we always ask for things with interesting properties. Primes are after all just integers with interesting properties of that they can only be divided by 1 and itself. So let's look at some primes with interesting properties. It turns out there are a lot of them with interesting properties that are primarily named after famous mathematicians. So let's look at a few examples. So first of all, we have Fermat primes. The definition of Fermat primes, a particular type of prime, is that primes of the form 2 to the power of 2 to the power of n plus 1. 2 to the power of 2, read it that way, to the power of n plus 1. And let's see if they're all prime. So we substitute in 1, and we find that this p1 equals 5, which is 4 plus 1, which is definitely prime. And n equals 2, p2 equals 2 to the power of 4 plus 1, which is 17. n equals 3, p3 equals 2 to the power of 8 plus 1. What is 2 to the power of 8? I'm pretty sure that is 257, which apparently is another prime. And the same is the case for n equals 4. p4 is a pretty big number, I won't list it here, but you just need to know that it is also a prime. What about n equals 5? Well, it turns out n equals 5, this number is equal to 2 to the power of 32 plus 1, which is not a prime, because someone found out that this number, 2 to the power of 32 plus 1, is divisible by 641. Imagine that endeavor, looking out for every single prime just to factor this monstrous number. So these are Fermat primes, and it is not known that there are any more Fermat primes of the form 2 to the power of 2 to the power of n plus 1 beyond n equals 4. So this is kind of an upper bound, and there is still a lot of verification to be needed because, as you know, factoring is hard. And you may ask, why do we need Fermat primes? What is so interesting about Fermat primes? Well, it turns out that Fermat primes have very interesting implications in construction. So let me explain a little bit here. This is going to be material for another video, but I can have some spoilers right here. I can spare some. So when we have a ruler, well, not really a ruler, essentially a straight edge, and also a compass, the thing that you can draw circles with. So that looks pretty abstract, but it's the limit of my drawing capabilities. So you might want to ask, what kind of shapes can we construct with a straight edge and a compass? Well, obviously you can construct a circle of arbitrary radius, and triangles and squares, provided that the triangle is equilateral, is also allowed. And have you ever thought of other shapes other than that? Well, obviously you can have a hexagon, because we know how to, well, I'm not really sure if you can construct a hexagon. I'm pretty sure that's the case though. And what about the 17-gon? The 17-gon, well, you might say that 17 is a prime, and it's not very easy to construct prime numbers. But is it true? It is true that we can actually construct the 17 gun using only a straight edge and a compass, these two tools we have here. And this is not a coincidence. It turns out that all the polygons with their number size of Fermat prime is constructible by a ruler of straight edge, although I wouldn't really think of a reason for you to construct this for n equals 4. It is really fascinating proof that it's not only geometry, also a lot of algebra, extended algebra that you're probably not familiar with, but just to say that if you're interested in how to construct a 17 gon using a straight edge and a compass, there are plenty of resources on the internet. And that's all about Fermat primes. Let's look at another type of primes, Mersenne primes.